Hello everybody, welcome to our Unit 5 review. Let's jump right in on slide number 2. Remember, slide number 1 is just a slide that has all of the information from Unit 5, so it'd be a good slide to maybe read over to help you prepare for your test. So let's look at this first problem that says, the diagram shows the graph of a relation R that maps set A onto set B. Remember, a relation is any set of ordered pairs. The first letter A says write down R as a set of ordered pairs. So notice that I use set brackets since we were asked to write it as a set. And then I went ahead and labeled all these ordered pairs. You don't have to do that. I just did that for our reference. And so I just listed the ordered pairs. Remember, each pair is called an ordered pair, so the order in the pair is important, an X value, comma, Y value. But the order in which you list each of these ordered pairs doesn't matter. So as long as you have these 6 ordered pairs, you could have them listed in any order, and make sure you use the brackets, okay? Then letter B says explain why R is a function from A to B. So I said it like this: every domain value has exactly one range value paired with it. There's other ways you could say it would pass the vertical line test. There are no points that would line up vertically, and the reason why is because there aren't any X values that have more than one Y value. Remember, it's okay to have Y values repeat, but you can't have X values repeat in a relation in order for that relation to be a function. Okay, then letter C says write down the domain of this function. Now, this function is individual points, okay? So when you list that domain, you should have individual X values. It's not a continuous interval of numbers from one number to another. It's individual, so make sure you have a list of individual. Now, you can list the elements of a set in any order, but it's good practice to always think smallest to largest. So I just read this graph from left to right, and I took the X values in order from left to right. And then the same thing with the range. If you don't have a green box, it could be that you have your range values in a different order. I listed them from smallest to largest, and you can just do that by looking at the graph from bottom to top and just pick up those Y values from bottom to top. One thing I want to note is that the Y value of 2 is repeated. If you listed it twice, that's not incorrect, but when you have a repeated element in a set, you don't have to write it more than once. Okay, so that's our slide number 2. Okay, slide number 3 says, asks us to state which of these graphs do not represent a function, okay? So I think on the slide I said write yes or no if they do. So I just realized that you might have opposite answers. But let's answer whether or not yes or no they are a function. So if you're looking at the graph, the easiest way to do that is to just use the vertical line test. If you pass a vertical line, I can't really do that, but if you pass a vertical line over this graph, if you ever have a vertical line that touches the graph in more than one place, you know that it is not a function. So I'm going to, just for clarity, I'm going to say this is not a function. I think on the slide, and on the class kick, I probably had you type yes if it is a function or no if it's not a function. So I guess we would say no, this is not a function, okay? Letter B would pass the vertical line test, and the reason why it's going to pass the vertical line test is that you never have an X value that's paired with more than one Y value. So that's yes, it is a function. Yes, it is a function. Okay, same thing with letter C. It would also pass a vertical line. Oops, that's not a very straight line, but these aren't very vertical either. But you would never have an X value paired with more than one Y value. Now, this is a function. Both B and C are going to have a lot of Y values that repeat, but you're never going to have an X value. If you were to list all the ordered pairs, you would never have an X value repeat. So we'll say yes, this is a function. Okay, and then letter D, a circle clearly is not a function. No, not a function, because it would not pass the vertical line test. Let's take, for example, 2. 2 has 2 different Y values associated with it. Okay, so if you have an X value that has more than one Y value associated with it, then it's not a function. Now let's look at slide number 4. It says for each of these functions, or for this particular function, defined by their graphs, determine whether it is many to one or one to one. Write down the domain and write down the range. Okay, so let's start with Is it many to one or one to one? So many to one means this one's going to be many to one because I can find a whole bunch of x values that have the same y value. So if you have y values repeat, it's many to one. Sometimes that seems kind of backwards to me, but many x values to one y value. So that means this one is many to, oops, not ton, many to one. Okay? And then II says, write down the domain. Okay, so it might be helpful to find the leftmost point, okay, and get its coordinates, -4, and then the y coordinate would be -8. And then this one is not going to have a rightmost point because that arrowhead, that means it continues forever to the right. So that means our domain values start with -4 and get bigger from there. So we would write the domain like this. We would say the set of all x such that x is greater than or equal to -4. Now I've seen some people turn that around and say -4 is less than or equal to x, which is not incorrect, but best practices, whenever you're writing an inequality that involves a variable, you want to name the variable first, okay? And then for the range, okay, so look at that bottommost point, and the y value of that bottommost point is -8. And then, since this graph levels off here, that means all of these points have a y value of +8. So that means our range goes from -8 inclusive, because there's a closed circle here, and then up to +8 inclusive, because all these points have a y value of 8. So that means our range would be the set of all y such that -8 is less than or equal to y, which at the same time is less than or equal to 8. And then slide number 5 is just like slide number 4. So let's start with determining what kind of function this is. Well, this again is going to be many to one. I guess one way to think about this is if this graph would ever fail the horizontal line test, okay, if you could draw a horizontal line where there are, and the horizontal line touches the graph more than once, you know it's many to one because there are many, more than one, or many x values that have the same y value, but it's still a function, but this is a many to one function, which, by the way, if a function is many to one, that means it does not have an inverse. Only one-to-one functions have an inverse. Okay, so the domain, it would be helpful to identify the leftmost point. Its coordinates are -3, -2, and the rightmost point, its coordinates are +4, +1. So to find the domain, read the graph from left to right, and it's going to be all x values from -3 to +4. Okay, so the domain will be the set of all x such that -3 is less than or equal to, notice they're closed circles, okay, so it's less than or equal to x, which at the same time is less than or equal to 4, okay? And then the range, okay, the range, read the graph from bottom to top. The bottommost point is here, and the topmost point is, oh, hold on, the topmost point is right here. So that would be, let's see, the coordinates are 2, 3, okay? So that means my lowest, my smallest range value is -2, and my biggest range value is 3. So the range would be the set of all y such that -2 is less than or equal to y, which at the same time is less than or equal to +3. And then slide 6 is more of the same. So letter I, this would be many to one again. If you use that horizontal line test, we see that the horizontal line would touch the graph more than once. So that means we have a couple of x values that have the same y value. It's still a function, but it's a many to one function. So letter I would be many to one, okay? II says write down the domain. So it would be helpful to identify this leftmost point. Its coordinates are, I think it's hard to read, -2, -1, -2, -1, and the rightmost point is at 1, 2, but one thing to pay close attention to is that open circle, okay? So that means when you go to list the domain from smallest to largest, you will include that left x value of the left endpoint, but you will not include the x value of the right endpoint. So the domain then will be the set of all x such that -2 is less than or equal to x, because we're including that x value, but at the same time it is strictly less than 1. Okay, 1 is not included in the domain. And then to get the range, identify your bottommost point, which would be this one, whose coordinates are -1, -2. Oops. Hold on. -1, -2, and then the topmost point is this one again, okay? So as you look at that, those range values, the smallest range value to the biggest range value, notice that this bottom range value will be included, but the top range value will be excluded because, again, of that open circle. So the range then would be the set of all y such that -1 is, nope, not -1. Wait, is that -1? I can't read the graph. Hold on, let me erase some stuff. No, it's -2. Uh-oh, I hope my class kick isn't wrong. Okay, that's the set of all y such that the y value of our bottommost point is -2. So the range would go from -2 inclusive, so that's less than or equal to y, and then up to +2, but not including 2. Okay, moving on to slide number 7. Let's see, it says the diagram shows the graph of the function y equals f of x. So letter A, we're going to find some function values. So for letter A, I, f of 4 is the output. Remember, f of 4 is your y value. It's the output when the input is 4. So when x goes into this function, it looks like that y value is 1. So f of 4 is 1. And then I, we're going to find f of -6. So when -6 goes into this function, it looks like a +1 comes out again. Oh, f of 4 is -1. I'm sorry. -1, not +1. F of 6 is +1. Okay, and then, I'm sorry, f of -6 is +1. And then f of +6, that's I. When 6 goes into this function, it looks like a +1 comes out. And then letter B says, find x if you're given the output value. Remember, f of x is what comes out of this function, and if what comes out of this function is -1, you need to find the x that goes into the function that produces a -1. So you want to find y value, any point or points that have a y value of -1. So it looks like there's one right here, and there's one right here, okay? So this one has 2 answers, and you can write that just by saying that f of x is equal to, you can just say -4 and +4, just list them in commas. Again, it's general practice if you have more than one solution to name them from smallest to largest, not mandatory, but it's a good idea. And then to find when f of x is -5, oh, oops, I goofed this up. Let me, sorry, this would be x is equal to -4 or 4. And then for letter I, when f of x is -5, so find a point or points that have a -5 for the y value. That would be right here. There's only one of them. So that x that produces -5 would be 0. And then for I, let's see, when f of x is 2, find a point where the output is +2. And it looks like there's one right here, and that x value is -7, so x equals -7. Then letter C says the point A, t comma 3, lies on the graph of f. Write down the value of t. So there's a point A that has a y value of 3. So let's find that. Let's see. Here's 1, 2, 3. It looks like it's right here. Okay. So that t value, the value of t, which is the input to the value to this function that would produce a 3 for y, it looks like that's going to be -8. So for letter C, t is equal to 8, And then letter D says, find the set of values of x for which f of x is negative. Less than 0 means negative. So I'm going to just grab a highlighter, and I'm going to highlight the part of the graph that's negative, okay? So let's find the x values. I'm trying to get a skinnier. Let's find the x values that produce those y values. Well, that would be from here to here, but be careful. Let me get a pen, something a little sharper. We want an open circle here and an open circle there, because notice it said f of x is strictly less than 0. So we don't want x's that produce something that's equal to 0. We only want x's that produce an output less than 0. So that would be from, let's see, what is that, -7 to +7? Oh, I'm sorry, I can't read this. So -5. It's -5 to, sorry, -5 to +5. So the x values that would produce output values that are negative, I'm going to write it in set notation. I'm going to say the set of all x such that -5 is strictly less than x, which is strictly less than 5. Again, you don't want to include -5 and +5 because f of -5 is equal to 0 and f of +5 is equal to 0. We want x values that produce y values that are negative, that are less than 0. Okay, then slide number 8 says, in a certain city, a travel card has a value of $150. Every time the card is used, $2.50 is deducted from the card. So letter A says, write down a formula for T of X, the amount of money remaining on the card after X times that it has been used. Okay, so if you think about this in terms of a graph, the y-intercept would be $150 because when the card has been used 0 times, there's $150 on the card. And then the slope, so that's going to be your C, that's going to be your y-intercept. And then this is going to be your slope, okay? But since 250 is being deducted, your slope is going to be negative. All right, so it looks like our function then would be, for letter A, T of X is equal to that negative slope. I'm going to write it in mx plus c form. So our slope would be -250 times x and then plus the y-intercept of 150. All right, and then letter B says find T of 6 and explain its meaning. So T of 6 would be what you get when you put 6 into this function. So -250 times 6 plus 150 is, let's see, that is equal to $135. So the meaning is there will be $135 remaining on the card. I guess I should write that down. $135 remains on the card, after 6 uses, or at 6 uses, I guess would be more accurate. Okay, then letter C says, find the number of times the card has been used when 105 is remaining. So T of X is 105. We need to find the X that produces that, okay? So make sure you write down this equation. Then from here, you can solve it any way you want. You can do it graphically. You can end solve if you haven't have an Inspire. Just make sure you show the equation. I'm going to go ahead and just solve it algebraically because I don't have a calculator handy at the moment. So this would be, let's see, -45 is equal to -250x. Divide both sides by -250. And x turns out to be 18, excuse me. So 18 uses of the card, is when the value of the card is $135. Then letter D says we're going to find the domain of our function. Okay, so the domain would be, now, a lot of you were trying to write intervals of numbers, but the domain values would be the number of times the card is used. Okay, the range value is going to be the value on the card. Now, you're not going to use the card like 1.5 times or 2.9 times, okay? You're going to use the card either 0 times or 1 times or 2 times, all the way up to 60 times, because if you plug 60 into this function, if you plug 60 in here, that's when T of X becomes 0. So that's your domain. okay? And then the range, again, it's going to be individual values. Now, some of you may have listed it like this, that the range is 150, and then after one use it'd be 147.50, and then the next use would be $145, all the way down to 0, and that's okay, but I would prefer that you always list or domain and range from smallest to largest. So I would go 0, that's after the last use, or 250, that's when there's one use left, $5. Oh, I guess you don't need the 0.00. I'm gonna not do that. It wouldn't be wrong if you did, comma, up to 150. Okay, so both of those answers are correct. It's the same set of numbers. I just prefer the second one a bit more because it's listing your range values from smallest to largest. Okay, moving on to slide number 9. It says Ezekiel walks from the park to home. After 7 minutes, he's 200 meters from home. So I'm going to write down the ordered pair, 7, 200. And then it goes on to say, and after 10 minutes, he's 80 meters from home. So I'm going to write down the ordered pair, 10, 80. All right. And then it says, assume that Ezekiel is walking at a constant speed. So eventually when we draw a graph of this, it's going to be a straight line because the rate of change is constant. So letter A says, find a model for the distance D from where Ezekiel is to home in terms of the time he's been walking T. Okay, so D is going to be, distance is going to be a function of time. So I'm just going to write that in general, our ordered pairs are T, comma, D, because distance is a function of time. Time is the input, independent, and distance is the output or the dependent variable. Okay, so to find that model, this is for letter A, I'm just going to use point slope form. You could do a linear regression on your calculator, but I'm just going to go ahead and do the algebra. So I'm going to start by finding the slope. So I'm going to take 80 minus 200 over 10 minus 7, which is negative 120 over 3, which is negative 40. So my slope is negative 40. So then I'm going to plug into this formula. This is just point slope in terms of D and T. So it would be D minus, I'm going to choose this point, D minus 80 is equal to my slope times T minus 10. So D minus, put this in point slope form real quick. I think that will be more meaningful for this context. Add 80 to both sides. So D equals negative 40T plus 480. Now you can either call that D equals, or you could write it in function notation and say D of T equals. Okay, doesn't really matter. Okay, letter B says, determine how far it is between the park and his home. Okay, so that's really asking us to find the intercepts, right? Because he starts at the park, so that's when T equals 0. So I'm gonna go ahead and put 0 in for T and find his distance from home at that time T equals 0. So that's 480 meters. So he starts 480 meters from home. Then let's put in a 0 for the distance. That's when he's at home, right? His distance from home would be 0. And let's find out what time produces that. So I'd have negative 480 equals negative 40T, and divide both sides by negative 40. So T is positive 12. Okay, so 12, now what are we measuring in? Minutes? Yes, so it's 12 minutes. Okay, so what that tells us, let's go ahead and write down the intercepts. So when the time is 0, he's 480 meters from home. And then when the time is 12, whoopsie, when the time is 12, oh gosh, hold on. Okay, erase, I don't know why that's not erasing. There we go. Okay, when the time is 12, that's when he's 0 meters from home, okay? And now I wrote that down because letter D says to sketch a graph of the distance for time for this suitable situation. sketch the graph of D for a suitable domain. Sorry about that. Okay, so I need a set of axes. Okay, now in this case, distance is a function of time. Make sure you label your axes. And let's come up with a scale. This is going to be kind of weird, but I'm going to count by fours. 4, 8, 12, okay? And I think for time, and then for distance, I'm going to count by hundreds. 300, 400. Okay, so that means, let's see, 10, 20, 30, 40. So that means my y-intercept would be right here at 0, 480. And my and I said y, I meant d-intercept. My t-intercept would be right here. And then if we were doing this paper and pencil, you would use a straight edge to make sure this is a nice straight line. So there we go. Okay, so you know what? I think I skipped letter C, didn't I? That was letter D. The graph is letter D. What did C say? Determine how long it takes. Oh, we already did that. Yeah, that was this part right here. This would have been C right here, where we found how long it takes for him to get home. Okay, I think we've done everything on slide 9, so we'll move on to slide 10. Okay, slide 10 says the exchange rate from pounds sterling, which this is the symbol that the book uses. I'm going to use GBP for Great Britain pounds. To Australian dollars, AUD, is that 1 British pound is equal to 1.73 Australian dollars. Okay, so letter A says find the number of Australian dollars equivalent to 70 British pounds. Well, if 1 British pound is equal to 1.73 Australian dollars, then 70 British pounds would be equal to 70 times 1.73, which is 121.10 Australian dollars. Now, let's talk about rounding. When it comes to money problems, for some reason in the IB, it's not really stated explicitly, but the 3 significant figure thing kind of goes out the window. So just make this a rule of thumb. Any problem that has to do with money, always round to the nearest hundredths place. If it were in US dollars, that would be to the nearest penny. Okay, so just always think nearest hundredths, unless you have explicit directions that tell you otherwise, okay? All right, then letter B says sketch a conversion graph for pounds to Australian dollars. Okay, so I'm going to set up and label some axes. So, let's see, this is going to be my input, which is pounds. And I'm going to, looking ahead a little bit, where I'm going to use P for my variable for pounds. And then this is, then my output would be the vertical axis. That's Australian dollars. I'm going to label that A. Okay, and then let's use a couple of points we know. Well, 0 pounds would be worth 0 Australian dollars. So I'm going to go ahead and use the origin as one of my points, and then we can use this point. Let's see, remember 70 pounds was 70. Yeah, pounds is the same as 121.10 Australian dollars. So, oh, you know what I forgot as a scale. So let's count Australian dollars by 50s. 200, 250, 300. Did I do that right? 50, 100, 100. And then let's count, I think I'm going to count by 20s. 40, 60. Okay, then 80. Okay, shoot. Okay, 80. Okay, I have a thing in the way. I can't quite write 80 there. Okay, so now, 70 would be halfway between 60 and 80. I should have counted by tens. That would make more sense. And then I'm going to go to 121.10. So I'm going to kind of guesstimate where that is. 10, 20 be about, let's see. I'm counting by 50s. So each of these is 10. So right about here-ish. Okay. And then I'll draw a straight line through those points. Okay, if I were using paper and pencil, I would use a straight edge. All right, so there's our conversion graph. Letter C says find a, so that was letter B. Okay, so we just did letter B. Letter C says find a model A of P. Well, A of P would be when we just take those British pounds and we multiply it by 1.73. So A of P would be 1.73 P. And then letter D says find A of 100. So we just put 100 in for P. Oops, 100 in for P, and that would be the decimal point 2 places to the right. So that would be 173 Australian dollars. And then we'll explain the meaning. The meaning would be is this is the equivalent to 100 Great Britain pounds. Okay. Then letter E says find A inverse of, I just wrote over that so I can't read it, A inverse of 50. So let's talk about what A inverse means. It's the inverse function of function A. So what does function A do? Function A turns British pounds into Australian dollars. So that means A inverse would do just the opposite. It would turn Australian dollars into British pounds. Function A takes P and multiplies it by $1.70, not a dollar, but 1.73. So the inverse of multiplying by 1.73 would be dividing by 1.73. So A inverse of 50 then would be to take 50 and divide it by 1.73 instead of multiplying. So that turns out to be 28.9, I think. Actually, that's 28.90. Oh, so I should be consistent. Let me go back to the part D, and let me change that to 173.00 to always round to the nearest hundredth. So 28.90, and that turns Australian dollars into Great Britain pounds. Okay, so the meaning of that would be this is the equivalent to 50 Australian dollars. Okay, is that it? Yeah, I think we have finished slide number 10. Okay, slide 10 or 11 says, Ben buys a new car at the same time as Charlotte. Ben pays 25,600 pounds for his car. Charlotte pays 18,000 pounds for hers. Ben's car depreciates at a rate of 1,150 pounds per year, and Charlotte's depreciates at a rate of 480 pounds per year. So it says use technology to determine how long it will take for Ben and Charlotte's car to have the same value. So Ben's starts at higher than Charlotte's, but his is depreciating faster, right? So if you think graphically what's going on here, you've got Ben's starting at a higher rate, depreciating quicker, and then Charlotte's, I said a higher rate, I meant a higher value. Charlotte's, so this is Ben's, this is Charlotte's car. She didn't pay as much, but hers is depreciating at less, her slope would be less steep. So, but there's going to be this point where they intersect. So you're going to use either Desmos or a graphing calculator to find the intersection of these two graphs. So we need, if we're going to do that, we need two equations. So let's just write it in terms of, I'm going to call Ben's car his function b of x, where b is the value of Ben's car, x is the number of years. So it's going to be, it's going to have a slope. I'm going to write them both in mx plus c form. So Ben's slope would be negative 1150. Remember, it's depreciating, so this is a negative slope. Negative 1150x plus his y-intercept would have been 25,600. And then Charlotte's c of x, hers would be, her slope is negative 480, again depreciating, but at a less steep rate, times the number of years, and then plus her initial value, which is 18,000. So you're just going to graph those two equations on either Desmos or graphing calculator, and then let the calculator find the point of intersection. And that point of intersection turns out to be, I think it was, let's see, something like 11.343 comma 12,550 555.224. Now, we're going to go to three significant figures. So let's see, what was the question? Let's see, how long it will take. Okay, so that would be the x value. So that's this value. So to three significant figures, that would be 11.3 years is how long it will take for them to have their cars to have the same value, and that value is going to be this y value and to three significant figures. Well, actually, it's money, so let's go to the nearest hundredth. So that would be 12,555.22, and this is in Great Britain pounds. There we go. So at 11.3 years, the cars will have the same value, which is this, which I don't know how that compares to $1, but that's pretty good value. If that were US dollars after 11 years, that's a pretty amazing value. But obviously pounds and dollars aren't the same thing. Okay. Now let's take a look at slide number 12. It says the first term of an arithmetic sequence is u sub 1 is 5, and the common difference is d equals 2.5. Notice this is a positive common difference, so that means the sequence of numbers will be increasing in value. Find u sub 2 and u sub 3. Well, that's going to be pretty easy because, I don't know what this is. Let me mark that out. Okay, because u sub 1 is 5, so to find u sub 2, all I need to do is take u sub 1 and add 2.5 to it, so that would be, what, 7.5? And then to find u sub 3, just add 2.5 to u sub 2, so that's going to be 10. All right? Then letter B says, write down the general term of the sequence. So I'm going to write it in general. It's u sub n is going to be the first term plus n minus 1 times the common difference. So that means for this particular arithmetic sequence, it's going to be u sub 1, we're told, is 5, plus we don't know the number of terms, but we do know the common difference is 2.5. Okay? So then to find C, it says find the smallest value for n for which u sub n is greater than 377. So we're going to make a table. So go to Desmos, and we're going to let n be our input, and then our output will be this. Okay, it's going to be 5 plus n minus 1 times 2.5. Now, it doesn't matter what variable you use, just make sure on your table that these match, okay? And then what you're going to do is just start punching numbers in until you get a number that surpasses, where the output surpasses 377. So I just made a table, and so I started punching numbers in for n. I punched in 100, oops, get a blue. Okay, I punched in 100, and I got, let's see, the table gave me 252.5. Oh, sorry, get the decimal point in the right place. 252.5. Then I punched in 125, and I got 315. Then I punched in 150, and I got 377.5. Okay, so the smallest value for n that's going to produce, and remember, n, the input of an arithmetic sequence, are integers. So the smallest value of n that's going to produce an output bigger than 377 is going to be 150. So for letter C, n equals 150. That's the smallest n that produces a sequence value that's bigger than 377. Okay, slide 13 on yours looks slightly different from this, but this is the gist of it. We have a sequence. Remember, a sequence is when you take the terms of a series. Sorry, I'm saying that backwards. This is a series. A series is what you get when you take the terms of a sequence and you add them together, okay? So letter A asks us to find the number of terms. So since I know the first term and the common difference, I'm going to use the formula for the nth term. So u sub n is the first term plus n minus 1 times our common difference. Okay, now I'm going to go ahead and take the nth term, the final term, which is this one, and I'm going to put it in for put it in for u sub n. So that nth term is equal to the first term of 20 plus the unknown n. I don't know what n was, but if we take n minus 1 and then multiply that by the common difference, you can see our common difference is 0.4. And then we'll solve that equation for n. Again, you can use any method you want to solve the equation. 20 plus, okay, n turns out to be 45. So you can n solve on a TI Inspire. You can on a graphing calculator. You could graph this, y equals 37.6, and then graph another line, y equals 20 plus n minus 1 times 4, and find their point of intersection, or you could do it algebraically, okay? But n is 45. Now, for letter B, then, it says find S, okay? So now that I know the first term and I know the last term, so I'm going to use this formula, the sum of n terms. Sorry, okay, be quiet, Siri. Okay, the sum of S terms is going to be n divided by 2 times the first term plus the nth term, okay? So that's going to be, we found out that n was 45. Our first term is 20, and the nth term is 37.6. So do that arithmetic, and the sum of those 45 terms then would be 1,296. Now let's take a look at slide number 14. It says, write down an expression for S sub n, which is the sum of the first n terms of this arithmetic sequence. So since I don't know the last term, I'm going to use this form, S sub n equals n over 2 times the first term plus n minus 1 times the common difference. Now, that's a formula you don't have to have memorized. It will be available for you when you take your test. But now let's use it to do letter A. So the formula for the nth term, I don't know n, I don't know the number of terms, but I do know the first term. The first term is 105. So that would be 2 times 105 plus, I remember we didn't know n, so n minus 1, and then times that common difference. Now, I'm going to put parentheses. Notice, be careful that the difference, since this is these terms are decreasing, the common difference is negative. It's negative 5. So I'm going to put parentheses around that negative 5 because I want to think about the way a calculator is going to think. If you just write minus 5, a calculator would think you're subtracting 5, not multiplying negative 5 times this set of parentheses, okay? So there's our expression. So then letter B says, hence, find the value of n for which, I'm going to write letter B down here. So for which S sub n is 1,140. So we're basically solving this equation. Let me just write it down. I'm going to go ahead and multiply 2 times 105 and make that 210 plus n minus 1 times my common difference. Okay, now, this equation would end up being a quadratic equation because eventually, if you were going to work this out algebraically, eventually you'd have to multiply this n term on the outside of the parentheses times an n term somewhere on the inside. So that means that you're going to have an n squared term. It's a quadratic equation. So why don't we use technology to solve it this way? And by the way, I kind of don't like eventually when we're using Inspires more often, I don't like using Inspires to end solve a quadratic equation because you have to do a little more work to find that second solution. Okay, let's talk about what's going on here. What I would do is I would just solve a system of 2 equations. I would let one of my equations be y sub 1 equals 1,140. That's going to be a horizontal line. And then my second equation would be, I'm going to write it in terms of x because that's usually how calculators want the variable, but I think on Desmos you could probably still use n. But anyway, I'm going to use x plus x minus 1 times negative 5. Now, that is going to be a parabola, and because of this negative 5, it's going to be a parabola that's upside down. So you need to find both points of intersection, okay? So graph the line, graph the parabola, find the 2 points of intersection, and those 2 points of intersection happen when n is 19 and when n is 24 is the other one. Okay, this is slide number 15. It says transfers from the airport to a passenger's house have different prices. Here is a table with some journey lengths in kilometers and their respective prices in dollars. Okay, so the first thing you're gonna do is plot a graph of this data on your GDC. Now, what you will put is you'll actually do it on Desmos and then upload a picture of a screenshot of that. But I just showed a hand-drawn graph here just to point out that you are providing a graph of this data. That's 1, 2, 3 points. So the picture of the graph that you put on your screen should only have individual data points that you're provided, okay? So that's the first thing you'll do. Then letter B says, choose an appropriate model for the price of this journey. Well, it looks to me that those points appear to lie on a line, so we're gonna choose a linear model, okay? And then letter C says, hence, find an equation for the linear model and then comment on your model. Now, this is where you will use this table that you've already put into Desmos and do a linear regression. If you forget how to do that, I made a video. It's linked to the calendar, so go back and watch how to use Desmos to use the Desmos to do a linear regression on those points to get a model. And so the model turns out to be y equals 28.6x plus 144, okay? I just use y. Notice I just use x and y. Since we weren't in the problem, we weren't given any particular names. We were given units, but we weren't given names for those variables, so I just use x and y. Now, I did do some rounding, and it's appropriate to round to 3 significant figures for your m and for your y-intercept, because later you're going to use that model to get estimates, okay? So since we're estimating anyway, this does not need to be exact, okay? So letter D then says, use your model to estimate the price of the journey when a passenger lives 27 kilometers for the airport. So that means you're going to evaluate, oops, wrong thing, hold on. Pen. Okay, so for letter I, you're going to evaluate y of 27. So just put that into your model, 28.6 times 27, whoops, not 72, good grief, 27 plus 144. Do the arithmetic on a calculator, and we will get $916. Actually, to be consistent with what I said earlier, let's call that $960.20. Let's always round to the nearest penny anytime it's a money problem, okay? And then for y of, y of 40, we're going to take 28.6 times 40 plus 144, and that comes out to $1,288. Let's go ahead and put the 00. Now, on Class Kick, I may not have done that, so if your boxes aren't turning green, that would be why. I'll try to remember to go back and change that, but just in case I don't, just heads up about that. Okay, so that's letter D. And then letter E says, comment on the appropriateness of your predictions from Part D. So notice that 27, okay, when we use 27, that does fall within the interval of our domain values, right? So you would say something like, it's appropriate for the, let's see, you comment on your predictions Part D. So for 27 kilometers, let me see if I can make some more room for us here. Okay, so for 27 kilometers, just say something like it's appropriate, because 27 falls within the domain values, okay? And then for, what's the other one? 40 kilometers, we would say not appropriate or risky, or, maybe less appropriate. It's not, there's not just one way to say this, but less appropriate because 40 does not fall within domain values or something like that. Okay, that's not the only way you can word that, but something along those lines. Okay, one more slide to go, so let's take a look at that. Okay, I thought this was the last slide, but I guess there's two more to go. So this is slide number 16, and it doesn't quite look like yours because I forgot to copy and paste the graph on here. So hopefully you're looking at your version of it because that graph is better. But this will do. So it says the number of widgets W that a factory produces after D days is given by the function W of D equals 0.25 D squared. And the graph of WD for D going from 0 to 6 inclusive is shown below. The first thing you're going to do is find W of 2. So when the input is 2, so find 2 on the x-axis, then you want to find the value, the y value there, the W value when D is 2. So now on your graph, it's going to be much easier to read, okay? And the coordinates of this point are 2, 1. So W of 2 is equal to 1, okay? Then it goes on to say that the range of WD is from 0 to 9, okay? So it says, from 0 to n, so hence find the value of n. Again, on your graph, you're going to be able to read this very, very well. So W of 9, oh, I just realized, hold on. Okay, I just realized this has a typo. This should be D, not 9. I think I was thinking about that N, and anyway, that should be the range of WD. WD ranges from 0 to N, so it says hence find the value of N. Okay, now remember the domain goes from 0 to 6, so when D is 6, then this point, which has coordinates 6, 9, would tell you what the max range value is. So the value, so when you put the maximum domain value into the function, the maximum range value that comes out is 9. So that means that n is equal to 9. Okay. Oh, whoops, there we go. Hence, find the value of n. Then letter C says, on the axes, draw the inverse of the function. Okay, now this is where it'll be much easier on your copy of it because you have a good graph. But I want you to do is find some pretty points. Like one of them would be this point, this 2, 1. Another one, I guess, would be, oh, shoot, I wish I would have given us more room here. 9, 6. Well, since I don't have room, I'm going to find another pretty point. How about 4, 4? So 4, 4. Now again, this will be much easier to see on your graph. Okay, so oh, you know what? 4, 4 isn't going to be a good point to use because 4, 4. Let me see if I can do this. I think I can scoot over a little bit. Ah, there we go. That's what I needed to do. Okay, so 4, 4 is going to be on the graph, a point on the graph and on the inverse. So let's go ahead. Let me go out to 8 and 9. Okay, so let's take the point, but this point 4, 4, let me go ahead and label that. That's going to be handy because the inverse should go through that point as well. Remember, the domain and the range of a function and its inverse switch places. So if the point 2, 1 is on a function, then switch those. The point 1, 2 will be on the inverse. So I'm going to graph the point 1, 2. Okay, so I know my function goes through the point 1, 2. It's going to go through 4, 4. It's also going to go through if the point 6, 9 is on our function, a point on the function, then switch those. The point 9, 6 will be on the inverse. So let me find that point 9, 6, and again on your graph this is going to be a lot easier. Now remember, let me get a different color. Remember that you should see symmetry in the line y equals x. Okay. Oh, that's not going to be quite right. Hold on, because my scales aren't the same. So let me draw that after the fact. Okay. So your inverse function should it should go through the origin, go through 2, 1, and then, oh gosh, it should, I guess 9, 6. Again, I didn't draw this to scale very well. So it should end up 9.6. I'm just going to cheat a little bit and move 9.6 right there. Okay, this is hard to draw by hand. This would be the point 9, comma 6. Now, you should be able to see symmetry in the line y equals x. Okay, that's a good check to make sure you've drawn the inverse function. Okay, so that was kind of a mess, but it should be better on yours because you have a better graph to work with. Okay, so we drew the inverse function. Then we're going to write down w inverse of 9. So if this is the graph of w, this is the graph of w inverse. So w inverse of 9 would be the output when your input is 9, so that's going to be 6. So w inverse of 9 equals 6, okay? And then it says, let's see, I gotta scoot this back over so I can read it. In the context of the question, explain the meaning of your answer in part D. Well, on our original function, w of d, remember d, the number of days, is the input. W, the number of widgets, is the output. So that's just going to be opposite for our inverse function. So for the inverse function, we're going to switch those. So the input is going to be the number of widgets, and the output will be the number of days. So in context of this problem, you could say something as simple as this. It takes 6 days to produce 9 widgets, okay? Now, if that were switched, w, the original function, w of 9 would be after 9 days, 6 widgets are reduced. Yeah, so that would switch. They would remember the domain and the range of a function and its inverse switch places. Okay, so now we have one more slide to do. Let's get to it. Okay, slide 17 says Debbie wants to borrow 1,800 Great Britain pounds or UK pounds and wants to pay it back over 3 years. She has 2 options. Option 1 is to pay a simple interest of R% per annum. PA means per annum, that's per year, so that's simple interest. And then option 2, pay the interest at a flat rate of 18% of the borrowed amount. So I just kind of made 2 equations here for us. For option 1, simple interest, remember simple interest is what you borrow times the rate times the number of years. So in this case that would be 1,800 times, now the rate is in percent, that's why I had to put R over 100, and then times the number of years. Option 2 is just that flat rate, okay? So if you were thinking in terms of a function, this would be a horizontal line, 18% of 1,800. So letter A says determine how much she'll pay back on option 2. So if we actually do the calculation and take 18% times 1,800, we get 324 Great Britain pounds, okay? And I went ahead and wrote it to the nearest penny. Well, it wouldn't be penny, but the nearest hundredth. Okay, then letter B says, find the value of R that makes Debbie pay back the same option for same amount for either option. So what we're going to do is we're going to look at these 2 functions and we're just going to graph them and then find their point of intersection. So you're going to graph the option 1 would be an increasing graph like that. Option 2 is a flat horizontal line, and you're going to find that point of intersection. So you would graph one line would be y equals 0.18 times 1,800, or you could just say y equals 324. And then this line would be y equals 1,800 times R over 100, because we have to turn that rate into a percent, and then times 3, okay? So graph those 2 points of intersection, and graph those 2 lines and find the point of intersection, which turns out to be 6, 324, okay? So that means that, remember, R, the input value, let me get a highlighter here. The input of this function is R, that's an interest rate. So this is actually, this is actually 6%. So your answer to letter B is going to be 6%. Okay, I hope you found this video helpful. Sorry, it's kind of a mess. If you have any other questions, be sure and contact me, and just want to wish you best of luck on your last test of the semester, which will be on Monday.